Okay, good afternoon, ladies and gentlemen. Welcome to the AWR ADF, the AWR Design Forum this afternoon. We've got quite a busy agenda. You might see the little flyers on the tables that I've put out. That will list what's going on this afternoon, and we're busy here until about 4 o'clock. It's quite important that we stick to that time. We have the happy hour downstairs from 4 o'clock to 5 o'clock, so it's important that we all get back down to the booth. Various presentations. Myself, I'm with AWR, as you might guess from the slide. I'm the UK country manager. I look after the UK and Ireland, and I've been with AWR for some 15 years now. Some of the following presentations will be by customers and others that are presenting on our behalf, some of the work that they've done. So I do encourage you to stay around this afternoon if you can. I'm going to be talking a little bit about the V13 release of the software. That's currently in beta format, and customers can get hold of that today if they wish. And I'll do a quick introduction, talk about what's new in version 13 of the software tool, and then if I can save questions and answers for the end, please. But I also encourage you to come down to our booth in the exhibition hall, booth number 4, in particular for some of Derek's work and the Antsyn demonstrations perhaps later on. We're very limited for time here this afternoon, so I won't be doing a great deal of active live demos, although I normally try to do that. For those of you that don't know, AWR involved in EDA, Electronic Design Automation, effectively an extra product today. We have microwave office and visual system simulator tools, circuit level and system simulation engines. We have planar EM simulation in Axiom and 3D FEM, finite element method solvers in Analyst. We have an RFIC tool for silicon germanium design in analog office. But also today, as from earlier on this year, we have Antsyn. It's a company that we bought out in the US. Derek is the head R&D gentleman here to talk to you later about antenna synthesis. And we'll make sure we cover some of that in this presentation. As you can see from the screen, global presence, I'm looking after the UK on both the sales and the technical side. We're directing France and Germany, Helsinki with the previous APLAC team. When we bought APLAC as a simulation company, we have all of those guys. And in fact, Heikki, one of the gentlemen here this afternoon, is the head of the APLAC team. What are we going to talk about? What's new and why we're evolving the software in V13 and what we're trying to achieve with that? Obviously, improving performance targets. They never seem to get easier. I wish they did sometimes. Increased integration. What we can get into a small physical footprint. As things are going up in frequency, size is easier to reduce, but we need to make sure that the circuits still behave in that small package. And some of the features that we've evolved in version 13 are specifically for that. Multitechnologies, some of the 5G libraries in the systems tool are aimed at better integration across the tool suite. Accelerating development costs. Making sure that time to production is much quicker, time to market is reduced. How have we done that? Performance through insight, trying to make it easier to drive the tool. Now, AWR, Microwave Office and VSS is known for being simple to drive, a very easy to use Windows interface. We've tried to improve on that user experience, make things easier to set up from the get-go, make sure that we have the next generation of components involved, PAs, filters and so on. And as I say, as from this year, antenna synthesis as well, and it all fully integrates into the tool. We can export that antenna synthesis design into Axiom, the planar EM solver, or into Analyst, the 3D FEM solver, and actually simulate the synthesized design. As you'd expect, working towards new system models, 5G models, phased array work in the systems world, where we're using a sample time domain engine, and how that all comes together and works side by side with Microwave Office. We spent a great deal of time looking at the integration of products. So we have our EM tools, but we also interface into CST, Microwave Studio. We can export the 3D designs into HFSS, and we can get into other engines as far as that's concerned. In terms of the EM extraction, I'll talk briefly about that. We have a technology called iNets, which is where in the layout side of the design, you physically click point A, B, C, D, E, and that ends up with a trace that runs potentially through board stack. So you can end up with wire holes, different metallization lines through the design. And we can reverse engineer that interconnect and actually end up with a touchstone netlist that will simulate that as a set of microstrip lines, wire holes, bends and corners. So iNets is not new, but it's all part of that technology and integration that we were focused on. Product development cycles, what else have we done? I spoke briefly about Antsyn, but another thing we've evolved is the iFilter tool, a filter synthesis suite. that we've had before, and we could do standard filter implementations. But rather than designing the filters, this is synthesis, and actually placing zeros at DC, infinite or finite zeros in the transmission characteristics, and synthesizing the filter from there. And again, like the antenna design, that exports into Microwave Office, allows you to simulate the product directly. Guided help is something we've focused on. I'll talk briefly about that at the end of the session. Guided help is the idea of using web-based pages, potentially on site if you need to keep them on local servers, or otherwise perhaps from our website, that will guide you through a specific design and design flow. So it will open the software, it will perhaps open examples to show you how that functions. It may even take you through steps to set up EM simulation, for example. And finally, there's a new wizard for component synthesis, mixers, multipliers, hybrid couplers, and so forth. Again, we'll generate the circuit, export that directly into Microwave Office, and within seconds, you've got a design you can actually use in real life. So focusing then on the performance, what have we done? More automation in the setup, and I'll show you some slides that justify some of this at the moment, in a moment. As you'd expect, the solve engines have, again, increased in speed. They're orders of magnitude faster rather than just a small increment in terms of speed. And that's on the harmonic balanced nonlinear circuit simulators and on the EM tools as well, both Axiom and Analyst. They've got massive jumps in terms of simulation speed. And I've mentioned the new models in the systems tool. In particular, we've done a fair bit of work looking at antenna arrays, particularly phase array antennas. We can simulate those with in situ measurements, so a circuit level signal producing a 3D antenna plot, and those antenna radiation plots be used then in the system tool as a measurement data file. So we can look at different directions of the phased array antenna, a signal perhaps on bore site, maybe a jam signal off bore site. And then what we do once we've got that data, how do we improve the access to that data? Next generation LoadPull, and we've taken LoadPull to the systems level as well, where we can look at system simulation, modulation schemes passing through a design, and vary the source and load impedance of the underlying amplifier in that systems level simulation. We can look at effectively contours for EVM or contours for ACPR type measurements. And better data extraction. On the graphs, we've got automatic ways of looking at 3 dB bandwidth, for example, monitoring and staying on top of peaks and valleys in a trace that are actively dynamic as you do things like tuning in the software. So specifically on the setup, the PCB Import is a massive improvement in version 13. There are several standards out there. ODB++ is one I come across regularly. The only problem that we've found with that is it's an evolving standard and keeps changing. Software vendors like ourselves are constantly playing catch up to make sure that we do and stick to that ODB++ specification. So what we've chosen to do is follow the IPC 2581 global standard. It's a lot more fixed. That is a superset, if you like, of the ODB++ files, and it allows us over either the advanced programming interface to import board designs. We can clip areas that we import and have specific areas around signal traces, for example, or bring in the whole board. And some of the EM simulation improvements for things like clip area take that into account. So we're able to bring complete boards into the design. And of course that flow works with some of the Cadence tool set, things like Allegro, Mentor Graphics and Zuken tools as well. So that should be a one-button push import and off you go, simulating that particular portion of the design in Microwave Office in this case. Open access, be it process design kits or otherwise, we can get into and use some of the open access database components and libraries. But Virtuoso, in theory, in ADS as well, although I'd like to encourage people to use Microwave Office over ADS or VSS over Ptolemy. And generate the app-like libraries from Spectre as well. So we interface into those tool suites that are available and customers might be using. One of the big things that we had to solve and resolve is the fact that the polygons that import in GDS2 world need infinitely thin cut lines to each of the internal shapes. In version 13 we don't need that any longer. What we have is the ability to draw internal shapes, modify those, move those around. So effectively a closed polygon with a cutout. Sounds like a small feature, but it makes a huge difference to the number of points on that polygon. And it doesn't start from A to B and end up back at A. It can have cutouts all the way through. And again, the small trace down on the bottom right-hand side, and we can add those cutouts as rectangles or imported shapes. And then lots of other changes to the actual simulation tool suite in terms of the drive. Two-tone analysis in the circuit schematics With process design kits, it might be gallium arsenide, gallium nitride, silicon carbide kits, custom toolbar buttons that can be fed. So for example, if you're using a Win Foundry process design kit, they can have on the toolbars things like run DRC, go and check for particular problems, do LVS checks and so on. Shape modifiers is something that we've introduced into the EM side of the software and will allow us to change and vary in the electromagnetic world things like registration of layers. So we can do yield analysis by moving layer registration, a processing problem perhaps, or etch allowance in terms of line processing, line widths and lengths, and allows us to look at that in the EM tool and generate yield data purely and directly from the EM shapes. Layout control pane obviously improved, partially extracted devices, all of these things have been added. Quite a lot of these come from customer feedback. So I don't know if you've used AWR, Microwave Office or VSS. We have a feedback tool called User Voice. Customers put in their requests. Those requests ripple up to the top of the request pile when we do implement a lot of those changes. One of those was to support touchstone data files with port names, for example. That's in version 13. What about the solve side? Well, it's a slide that I show year after year. The AppLac harmonic balance engine and time domain engines have got faster. I think as a simulation company, if we didn't do that, we'd probably go out of business. So they have improved. But if you're not aware, we have a specific patented engine called transient assisted harmonic balance. If we have a particularly difficult harmonic balance nonlinear problem to solve and the engines aren't converging, we can run off and do some time domain analysis on that for a few cycles, use that result as the seed data for the harmonic balance engine, and start to use that engine then given some prior knowledge, if you like, on the transient results in the first instance. That's something that's patented against AWR, and that, of course, has improved all the way along. And as I mentioned, both Analyst and Axiom, they've improved not a small jump, 20% faster in some of the simulation runtimes. We're using multi-cores and multi-machines, potentially over floating networks. Easier access to the port data. Things just keep getting better. In my background, I was with Marconi Instruments, so I'm used to microwave component design, circuit level components design at hardware level. I'm not really a systems guru. I know some of the VSS capability. On the systems side, sample time domain tools, of course. We have a lot of the modulation libraries that are used in the simulation world, but now at its extracted level. So if you have amplifiers, for example, in Microwave Office, they come up as a behavioral model into the sample time domain world. You can have printed filters or surface mount component filters in the sample time domain engine, running sample time domain engines on the frequency domain results. That's all extracted automatically for you. As you might expect, we've generated and have new 5G waveform libraries. We have the LTE Advanced library that has come across and been implemented, both downlink and uplinks. And signal I/O enhancements as well in the system tool. A screen grab there of a multi-channel library signal. I alluded to and mentioned some of the antenna array improvements. Now that is several levels. It's at the electromagnetic level. You can see here that we're, oops, there we go, wrong button. See here we're actually looking at the beam pattern, but also steering in pretty much real time the beam pattern and how that is generated based on the feed signals. And that feed pattern array of data can be taken into the system tool and used as an antenna specification and used in the systems world. And that can be both transmit and receive antennas. So you can have that in dynamic access. Of course, that applies to automotive, 802.11p, car to car, applies to military EW type radar systems as well. VSS as a systems simulation tool can get as complex as you like. This is a quick screen grab of a particular 5G modulation scheme being generated, looking at the bit error rates, the different types of modulation, algorithms that can be used and the trade-offs, very appropriate for some of the MIMO applications. And as you might know, as a subset of National Instruments have USRPs, radios that can be programmed from LabVIEW. Now you might appreciate that LabVIEW and VSS will run side by side, but of course these signals we generate in VSS can directly drive PXI hardware, and that includes the USRP radios as well for MIMO work. What about the access in terms of data access? We've done a lot of work with LoadPull, that's both focus and Maori, measurement LoadPull data sets, multi-dimensional interchange format arrays. Those formats can be applied to electrical simulation models or swept in simulation. It doesn't matter whether you've got measurement data or you generate those data points on both load and source pull gamma points, and lots of measurements therefore simulated based on that particular gamma point. It's not obvious from the graph, but some of these measurements are dynamic. So we have a marker here on this load pull point or source pull point, and the gain contour curve will become dynamic as you change that impedance point on the Smith chart. So as you left mouse click drag around the impedance point that you're offering or the load point that you're offering on a design, you actually see the active curves change and update. Very, very useful. We've taken that one step further with version 13. We've actually allowed the system tool to access some of that impedance point data from the circuit level tool. And we can start to do, and I still have trouble getting my head around this, the idea of contours on system measurements. So adjacent channel power ratio, EVM measurements, and use the system tool now to use varying load and source impedance points in the measurement and the simulation data in the systems world. You might see on some of these slides, I've linked to certain presentation examples. I would like to show those live, and I would normally do so, but we're limited for time. So I'd encourage you to come down to the booth. We're on booth number 4 downstairs, and I can show you those if there's something specifically that you're interested in. And finally, I mentioned in terms of accessing data, enhancements in the graph marker system. We can look for a specific peak valley, particular bandwidth, and that's dynamic. So as you were to perhaps automatically tune or optimize a filter design, of course that marker measurement system continues and automatically tracks that result. So you can keep an eye on package resonances, you can keep an eye on filter bandwidths as perhaps the optimizer is working, for example. Another improvement in version 13 is what we call matching waveforms. Now, I first thought of time domain simulation waveforms when I thought of that. So as time progresses, real time, you see the waveform appear. But we do the same with the harmonic balance engine as well. So if you have multiple frequency points, if you've got multiple power levels or test levels, you'll see those waveforms appear as time progresses. Quite often very beneficial. I've waited perhaps a few minutes for a simulation trace to generate. Now you wait seconds for the first few points, and if you happen to have left something open circuit, you'd see that within seconds rather than minutes. So a very powerful way of doing things. You see that data progress over time and end up generating your full trace as we used to have in earlier versions. What about multi-technology? We've done a lot of work in version 13 on multiple technology. I know you would expect that to be the case, but the idea now of dragging in designs from different departments, and that could be different engineering departments, be it MMIC, RFIC, bulk acoustic wave or surface acoustic wave files that are brought in, and they're all generated into the same design. That one I certainly have running live here. Let's see if I can find that. This idea here, we'll stop that spinning around. And what you might see, what you might see in there is several sections of design, some perhaps at silicon germanium level, right down to FET fingers, some perhaps on gallium arsenide, different amplifier stages. In this case, it's a cell and wireless LAN transmit card. And what I'm trying to show on the top left-hand side is we have the generic laminate layer technology file alongside the MESFET, the BOR, and the SIGI kit as well, all in one project. And that's something that we feel is critical. Looks easy to do. It now means that we have to export gas masks and silicon masks for the correct parts of the circuit, and of course we've taken care of that. Very appropriate for module work, of course, as well, when you're looking at laminates, low temperature, high temperature co-fired ceramics, and it works across those EM sockets that I've mentioned, so the idea of exporting into and out of HFSS, CST tools as well. I mentioned the shape modifiers, a quick picture of the sort of thing that I'm alluding to here. So this is an EM design of the front end of a matching network. This is on a multi-layer laminate with this specific inductor through the board layers you can just about see here. And what I've done is with shape modifiers, I've played around with the registration alignment in the processing, the manufacturing stage, and asked it to go through and sweep that registration, give me multiple EM simulations. You can see it offset here, the layer registrations of that spiral, and of course generate the results and a yield data type format to show us the spread of a likely production across that, but this is whilst running EM simulation. About the best results you can get, but also taking into account manufacturing. I go in and visit a lot of customers in the UK, and all too many of them are using the nominal ideal design values, something you can never actually physically make. You might make it one perhaps in a million runs, but that ideal one is one that you always allude to and can never actually reach. So it's very, very wise and very prudent to look at manufacturing tolerances. I mentioned the connections with the likes of HFSS. So we have a design there, a ball grid array, flip chip mounted design. All of the bond wires there as well. And if we have that in our 3D EM tool, something like Analyst, we can simply design there, or indeed with several mouse clicks, right click, EM socket partners, export to CST, HFSS or Sonnet, and you have exactly the same design passed across. All of the S-parameter files are passed back into Microwave Office and plotted in exactly the same way as though it was part of our simulation engine. That's really quite critical, and the way that works. I've got another example just here, if I can find the right one. So in this particular design, I was looking at a multi-technology type design. The idea is we have the matching circuit on the laminates, we have ball and stitch bond wires up onto a chip, multi-layer technology for the gas FET fingers as well as surface mount device chips. And what we were looking at on here is the idea of running not just the circuit level tool, but EM extraction. And at the top level here, you might see that these extract blocks point to different engines. So we've got the bond wires going across to our 3D EM simulator. They're extracted automatically in the results used. We have the planar chip interconnect, all of the layout interconnect on that chip sent out to Axiom. That's our planar tool, which is appropriate for that work. And then we have some of the matching network extracted to an ACE engine. And it makes quite a large difference in the way that simulates and how it works. So for example, here are the ball and grid wires. We look at the mesh, you can see that that's done in a true 3D FEM finite element method solver. That's appropriate to the bond wires, but just the bond wires in this case. You'll see sitting down here we have the, wrong one, this one over here. We have the surface of, sorry, there we go. That's the one I needed. But slightly small on the screen, sorry. That's the surface of our chip design with a spiral. We send that out to a planar tool. So in 3D you can see two things. We actually simulate the thickness of the metal, and we simulate that with now a planar solver, so triangular mesh. And it's done across all of the interconnect on that design. The color coding here is the DC connectivity. And then for the interconnect on the matching network, that was the last one that I had there, that's effectively done through ACE extraction. We look at the tracking and get an equivalent net list for circuit level linear components. And all of those come together to give us a result. That result will certainly give us one level of gain. Here we go. If I freeze that trace, turn off the extract blocks, so we go back to circuit level models. There we go. Turn all of these off. What we end up with is with a simulation of closed form electrical models, but based on electrical simulation of them all being isolated. And you can see very definitely there are differences in the results. So it's very easy to take a design, take that layout and throw it at the correct engine. So when I speak of EM extraction, that's the sort of thing that I mean. When I speak of sending it through to our 3D EM tool or HFSS or CST, it could be any of those engines. Accelerate design cycles. I spoke of several tools that we have available in version 13. The Antsyn technology, which I'll introduce you to Derek in just a moment. The iFilter tool that I'll finish off with, and looking at guided help and component synthesis. All wizards, so certainly on the iFilter side it's a wizard in the wizard's tree branch that you get access to with inside Microwave Office. The Antsyn is a slightly different tool, and I've got the pleasure of introducing you to Derek Linden. He's the head of R&D from the X5 Group, a company that we bought earlier this year and is now part of the AWR toolset. Of course, they're also now owned by National Instruments. And rather than me give you a fairly elementary explanation of the antenna synthesis tool, perhaps Derek, if you'd like to come up and chat, he can give you a proper explanation as to what's going on.
Thank you very much. So what we have is a cloud-based tool, and this can now also run in on a company's intranet behind their firewall if desired. And what it does is it automates the antenna design process. So you can actually have people who are systems or RF engineers able to design antennas, as well as having experienced antenna designers to be able to make much more rapid progress and gain much more insight into design challenges. In this software, you define your performance requirements. You don't enter a model directly. You enter what you want the antenna to do in terms of frequencies and pattern and gain, etc. And then we have an evolutionary algorithm that performs optimization and that continually generates better and better models based on your specifications. It's very scalable with compute power, so that if you have lots of design challenges or the challenges are very difficult to solve, you don't have to hire more and more engineers. In fact, antenna engineers are very hard to come by. It's much easier that you can just expand your compute capabilities. It has ability to generate new antenna designs automatically, kind of does an automated invention for some antenna types, and it's pretty easy to use and intuitive. At least that's the goal. And we have lots of antenna styles in our library, and that's continually growing. And some of those antenna styles are very textbook type, and some are very, let's call it under-constrained. There's lots of different possibilities that are there. For instance, mesh. Some of the things you'll see in there are mesh-type antennas where wires or plates are switched on and off by the algorithm to come up with these unique designs. And once the designs are created, they can be exported into Analyst, Axiom, CST, HFSS. So here's an example. You enter this is their spec sheet, and it's kind of like if you're going to hire an antenna contractor, you give them the frequencies, you can determine what your return loss is, you can even program in stop bands if you need to, say, filter interfering frequencies. You can put in your pattern requirements where you want gain maximized and minimized. We also have a place where you can put in your geometric environment, the constraints for the antenna in terms of size. And then, as I was saying, you can select antennas from this library of antenna templates, or you can allow the system to do it for you. And some of these antennas are fairly regular in textbook type, and then some are decidedly really kind of computer-only type models. You can also co-design matching networks or phased arrays. And once you run the spec sheet, you can get lots of designs out. Now you can pre-select certain designs, and you only get a few of those. But if you allow the system to select designs for you based on your specs, it usually tries to cast a very wide net over the different kinds of designs that are appropriate for your spec, and you can get a really nice trade-off between antenna designs that maybe look sort of like what you would expect, and some that maybe are very unique but have some qualities maybe that are desirable. And you get a chance to see how these different designs behave. We give you a dashboard of results, and then you can export those to your tool of choice or to your various CAD tools. So you can either go directly into building, or you can do further simulation. As kind of a quick overview, any and all questions, please come down to the booth, and I can give you much more detailed demonstration and hopefully answer those.
Thank you, Derek. Yes, as Derek mentioned, I was aware that we would be short of time today, so I do encourage you to come down to booth number 4 in the exhibition hall and watch that live. It needs to have a web connection, but we've got that downstairs. This was an example of one of those synthesized antennas, an ultra-wideband planar antenna. The tracks are on either side of a piece of board. The radiation pattern that's simulated in Axiom, and the measured versus simulated data in pink and blue trace on the top right-hand side. Pretty close. The iFilter tool, we've improved that. I mentioned that we have the filter synthesis tool already in version 12. For version 13, we've added the ability to place zeros. DC, finite zeros, infinite zeros, and physically design the filter based on those locations. As you see from the screenshots, we can add those zeros, end up generating a circuit diagram, and that's exported directly into Microwave Office to build the filter. What it is an ideal filter synthesis tool, so you'll end up with a lumped element equivalent. It can be planar too. And of course, the planar technology, if it were microstrip, would end up with a printed filter you could physically manufacture within a few moments. The last thing I wanted to leave you with is some of the improvements on how to drive the software. We've done two things. We've added guided help, which is really quite useful. The idea is on a web page, and this can be customer-based or it can be based on help that AWR gives you. We have web pages that guide you through how to do a design. So it could be how do you set up the EM tool, for example. That's this particular one here. A bit of text and then a button to press, open the EM structure. And it will go away and open Microwave Office, generate the EM design, add your ports, talk about how to simulate at particular frequencies, how to generate the graphs, and a very interactive way of doing design work. Now we can use that to teach you how to use the software. It's easiest for us to write help that way. But of course, customers could do things like an amplifier build book that way in the same manner. And finally, a wizard. This has been written by Dr. Stephen Muss over in the US, looking at mixer multiplier setups, looking at microstrip properties, be it lange couplers, branch line couplers, and so forth. And the minute you click on those buttons, behind the scenes is generated an electrical circuit schematic. Because Microwave Office has the layout attached to that, you end up generating the layout immediately, and a design you could go to manufacture within a few moments. So lots of help on how to drive the software again from that point of view. Now, I'm very aware of the time. I'm afraid I've run out from my slot. Version 13 is available for you to play with if you want to. Today, the current build production release is 1203, sorry. But if you wanted to play with version 13, please come and see us. We can give you access either to download the software or provide it to you on a dongle key on the booth stand there. Perhaps if there are any questions, I can take those quickly or hand over to our next presenter. Thank you.